This work is about neural surrogates. We're building a neural network surrogate models for Bayesian optimal experimental design problems. So to start, I have to say I learned quite a bit for the optimal experimental design from early times of Rao's work and your group's work. I still remember at the time, I think it was 2012, that I went to the course. It was a very interesting experience, and I learned quite a lot from you on many different topics. So today, we're going to present, this is a specific topic, but it's not going to be a very specific paper. It will be a survey of a few different papers that we've been working on. Some of the recent ones, some of the a bit old, a couple of years ago. So this is joint work with my previous student, Jin Go at Georgia Tech, and Rafael Oranzo and Felix Herman, and my colleague here at Georgia Tech. And some of the work from previous institute that I worked on with Kei Wu, who is in Meta now, and Thomas O'Leary Raspberry at UT Austin, and Omar Gattas. And then there's some joint work with Nico Areza from UT Austin, and Dennis and Degan at Aachen, and Karen Roy on reduced basis approximations. Okay, let me get started. I'd like to give you a few different examples for the experimental design. The first is a tsunami warning. So as you can see here, we have a tsunameter here to detect the earthquake. And once there is earthquake, it's going to send the acoustic wave and to the surface buoy. And then, from the surface buoy, it can send a signal to the satellite. And then the signal will be passed to some stations for the early warning of the tsunami. As you can see here, once there is earthquake, so this can be properly detected by the tsunameter. But the problem is, where to place this tsunameter, right? So here the data we collected are the acoustic wave detected from tsunameter and surface buoy, and uncertainty is a slip along the earthquake fault, which generated the tsunami, right? Which is a stochastic process, and it's both space and time dependent stochastic process. So well, to properly model this system, we can use a coupled elastic acoustic gravity wave equations for the propagation of the water, from where it's got excited to the coast city. Let's say we can use shallow water equations. This is one of the simulations on the acoustic gravity equation where it's got excited from here, and then it's going to get away from this center. The optimization problem is to optimize the information gain we get it from this is tsunameters. So the specific optimization problem is where to place all these sensors. We need to place them in a strategic locations, right? So which can maximize our information. Another example is optimal experimental design in medical imaging in MRI. So here, what you can see is we want to do a MR examination for the knee of the patient. So there is a strong magnetic waves here sent from here. So you can receive the signal in this device. This is a receiver on coil. But of course, we want to maximize information we get it from this process and want to reduce the examining time. And there is a large data set. It's called a fast MRI, open data set, where we can build on this data set to use some machine learning and technology to accelerate this process. So for instance, once you get imaging, the signal is essentially is in the K space, so-called frequency space, with a Fourier transform. Here, this is the fully sampled data. So essentially, for a long period of time, you can examine the patient with the knee part, and you can collect a lot of data. But however, if you want to reduce the amount of data, let's say instead of this amount of data, we want to use maybe 2% of the data. And so this can significantly reduce examining time, right? So where to get this 2% of data? By the way, so this center is corresponding to the low frequency mode. And if you go out the center, it corresponds to the high frequency mode. A naive approach would be, taking some of the low frequency data here and randomly sample the high frequency data. But this is not optimal. So recently we developed a approach which is a probabilistic Bayesian optimal experimental design. Essentially, we take uh, here all this data in a probabilistic way following a Bernoulli distribution. And we can calculate the optimal density. Like here, this is learning the probabilistic density. And then we can draw the samples from this density. So here are the corresponding samples of the data that we collected. Um, well, to do this optimization, we use the so-called conditional normalizing flow. This normalizing flow, is built to map some reference measures to their target measure, which is our posterior probability distribution. And this posterior probability distribution depends on our optimal design or our design. So we can optimize the neural network to approximate the posterior distribution, and at the same time, we can optimize our design. So this is joint optimization problem. Um, well, here you can see this is a reference image. If you draw, the data like this, the handcrafted baseline and design, you'll get some posterior samples like this. It's quite blurred. It's a bit far from the reference image. So now if you apply our recent developed methodology, then the posterior sample actually looks quite like the reference image after the optimization. I will not focus on this part of the work, but rather on the neural surrogate to accelerate the forward model. So here's another example, which is an optimal experimental design for monitoring the tumor growth. So what you can see here is the two set of data with the corresponding red 1 and red 2. So for two reds, right? So you can do their diffusion weighted MRI to see so how much the tumor growth over a certain number of days, like day 10 up to day 20. You can see, I can collect the data essentially um, to monitor the growth of the tumor. And then you can solve a certain inverse problem. Let's say we have a forward model, which is a diffusion, a nonlinear reaction model that can model this tumor growth. And then we can invert for some parameter in this model. And this parameter will reflect the growth of the tumor. So now the problem is when do we collect the data, right? So let's say here we have about 10 days. So out of the 10 days, whether they're optimal 3 days or 4 days that we can collect the data that can best inform the tumor growth. Of course, you can collect over all days, but it's quite expensive. And well, specific questions sequentially, which are the days you're going to collect, right? This is another corresponding red. As you can see, there is certain variability in this process. Um, so also, we developed some, framework of a sequential infinite dimensional Bayesian optimal experimental design, where the parameter is actually a field variable. And I'm going to talk about this part a bit later on. But essentially, as you can see, this optimal experimental design, it could be either static, you just design, let's say, where to collect the best data, right? Or where to collect, data from the sensors of the sonometer once you place it and you can keep it over there. Or it could be time dependent. So you're going to pick which days you're going to image, um, the tissue or the tumor. So it's experimental design both in space and time. All right, so here's the basic setup. So in one of the cases for the spatial design, the problem is where to place this R sensors out of D candidates. Let's say here we have D candidates. We want to place R sensors. Like in this particular example, we have a 9 candidate places. We want to place 3 sensors, right? So there is a corresponding matrix W. Let's say in the first row here, in the corresponding third column, we have a 1. Essentially, out of this 9, candidate sensor in these 9 columns, we pick the third one. This is the third one as our first sensor, and so on and so forth. This is our design matrix. So it's binary matrix. And this F is our forward operator. It's from our parameter to our observable. This D stands for we have all this D candidate observables, and we're going to pick our sensors out of it. So this is the basic setup of the sensor placement problem. And then so to optimize this sensor placement, we need a certain optimization criterion, optimal criterion. Here we denote it as a psi. Psi depends on the design matrix W. Well, there are many different kinds of optimality criteria in the statistical literature, and also recently studied in their, in the literature constrained by larger scale models, simulation-based optimal experimental design. Some of the early work from your group, you know, like much better than I do, but I studied quite a bit on this reference and also some follow-up references on important sampling on Laplace approximations. There is another class of optimality criterion which use expected information gain. So you can use some polynomial approximations, and then also some recent work on infinite dimensional expected information gain, where you can leverage some low rank property. So one of the criteria here you can see is expected information gain, where you have W is our design matrix and Y is our data and theta is our parameter. So we have a posterior here, we have a prior distribution. We want to measure the difference between them, the Kuebec-Leibler divergence between this prior and posterior, and then we can take the average with respect to our data. This is expected information gain, and also some covariance-based, so-called A-optimality or D-optimality. It measures the trace or determinant of the posterior covariance. Like here, we have a posterior covariance in the Laplace approximation. It depends on data Y and design W, right? We can take the trace and average with respect to our data Y. And similarly, we can also compute the determinant or the log determinant of the prior the inverse of the prior, you take the square root of that and precondition the posterior here, and then you can compute the log determinant of it. So these are some of the criteria. So let's say for the expected information gain, a bit of a the sample average approximation or nested sampling approximation, where you have a the Kyle divergence and you take expectation with respect to data Y, and it can properly approximate it by this double loop approximation. So in the out loop, you draw samples from your data, right? These samples follows your model evidence or the marginal likelihood for your data. You draw samples from your data. There is corresponding parameter theta I too. And then in the inner loop, you want to compute this model evidence term or normalization constant, where this normalization constant is the integration of the likelihood with respect to the prior. So you can draw a lot of samples from your prior and compute this average of the likelihood function. And apparently, for this approximation, you would need in times for the evaluation of the inner loop and n out times for the evaluation of the out loop. And in total, there will be n out by n in times evaluation of your likelihood function, or if it is a model constrained, and then you're gonna have to solve this many times the forward model. And so this evaluation is for each experimental design, right? So the problem is when the likelihood is locally supported, which is often the case in high dimensions. Like this here, even in these two dimensions, you can see this likelihood function is relatively locally supported. You need to draw a lot of samples from the prior in order to properly capture this distribution and to evaluate this model evidence term, right? So then each model solve could be quite expensive. It's constrained by larger scale PDEs, for instance. There are different methodologies to approximate this EIG criterion using some of their density estimate with a surrogate in variational inference, or you can propose some like important sampling based Laplace approximation of the posterior, and then can draw samples from this posterior as quite interesting. So here in one of the work, we use the reduced basis approximation for the forward model, and our optimality criterion is slightly different from this EIG or D-optimality, but rather it's a stability-based optimality, and we use some greedy algorithm to solve this problem. This is on the reduced basis approximation. This is not a focus on this work. But let's say if we want to evaluate this EIG, right? So this model is quite expensive. Using neural surrogate, we can also approximate this from parameter to the observable map very fast with relative high accuracy. So let's say here we have a map. This map is going from our parameter to the observable by a certain neural network, like we denoted as a neural network, parameterized by some neural network weights W. And over the years, there are several different classes of neural operators. You know, if theta is a function and the output observable is also a function, then it is a sort of like an operator. So there have been a few classes of neural operators to approximate this map, like a Fourier neural operator or deep operator network, DeepNet. And also there's a certain class of reduced basis architectures. So you can reduce the input of the parameter theta and also the output of the observable. There's also several different work using this reduced basis architecture like a neural network ROM or POD, deep learning ROM, PCA net essentially perform the PCA for the input and output, and also develop this derivative informed and projected neural network, and also some autoencoder. Um, Instead of the linear dimension reduction, you can apply this autoencoder using the convolutional neural network. Okay, so there's a couple of papers on the comparison of this different architecture. One of the conclusions is, if you are in high dimensions for large scale problems, and then if the map F lives in a low dimensional manifold or intrinsically there is a low dimensionality, then this reduced basis architecture tends to perform better. Um, from the perspective of cost accuracy trade-off. I'm going to explain more detail later on about this cost and accuracy and trade-off. But essentially, in high dimensions, you want to leverage this reduced basis architecture. So here's one of the architecture that we propose is a DeepNet, derivative informed projected neural network. So for the input, we use some encoder. For the output, we use some decoder. And in the encoder, you can use, let's say, PCA or some convolutional neural network. But specifically in this work, we applied, this derivative informed dimension reduction, or it's related to this active subspace. You compute the derivative of the output with respect to the input, right? And then you form this gradient information matrix. You compute the eigenvalue of this gradient information matrix, and also the corresponding eigenvectors. These eigenvectors will serve as a projection basis for our encoder. And for the decoder, we can also apply similar derivative informed basis or the PCA or POD, for instance. So then we can, reduce the large map from the input to output as a relatively small map in their small dimensions. Let's say here we have the dimension maybe 1 million. Here we can reduce it to about 100. So our neural network will only operate in their 100 by 100, input output map. So specifically, the neural network is given as you have the input projection with a basis of V. So you have Rx for the input dimension reduction, which is the dimension for the input. And also you have the U of Ry for the output and projection basis. In between, you have a relatively small neural network phi. Okay,
So in some
so yeah, go ahead.
sense, this is like an active subspace, and then you apply the ResNet, or like a retrogression, and then you apply the ResNet. Could we think of this in this way?
Yeah, it's pretty much yeah. Well, let's say, well, actually the importance is actually coming from the active subspace. Active subspace can give us the most sensitive dimensions. Um, and compared to PCA, for instance, in our paper, you can significantly reduce the dimension of the input dimension. And for the output dimension, actually, either a POD or the active subspace for the output, if you do the Jacobian transpose Jacobian, and the other way around is Jacobian transpose. You can compute both the input basis and output basis. But for the output basis, this derivative doesn't really help too much. But for the input, it helps a lot.
Thank you.
Yeah, thank you. So for one of the example, let's say we have a diffusion reaction, convection and reaction with nonlinear reaction term. We have a coefficient e to the power of theta. Theta follows some Gaussian distribution. It's got a covariance as this so-called Martin type of kernel, where we have the Laplacian with certain parameters delta, gamma, and alpha, which measures, which dictate their smoothness, correlation length, and variance of the random field. So let's say here we have one of the prior sample, and this is our solution, the state variable, where the velocity field comes from a solution of the Navier-Stokes equation, steady state Navier-Stokes equation, and we have a certain number of observations, like here about 100 observations, right? So we want to select a certain number of sensors from it. Um, well, if we directly apply, let's say, this neural network input-output map to compute this EIG, where we can simply plug in our observables F in our essentially the likelihood function, then we can evaluate this double loop map. So here's a sort of like the comparison. So we can apply our deep net double loop Monte Carlo. Essentially, we first construct this neural network surrogate, and then we apply this double loop Monte Carlo because each of the evaluation is relatively cheap, right? So then we also compare against if we do not construct this surrogate, but rather we can use the same amount of computational cost to evaluate this double loop Monte Carlo. And this is a relative error of our EIG. So as you can see, with increased number of sensors, the relative error computed by this neural surrogate remains to be relatively small compared to if you directly apply this double loop Monte Carlo with the same computational cost. And we have some error bound. The EIG error can be properly upper bounded by the neural network approximation error in L2 norm up to a constant. Um, so this is one type of a neural surrogate. It's quite simple. What you do is that you directly apply this input-output map in the evaluation of the double loop Monte Carlo, or in the evaluation of the observable, right? So and then there is another class of approach which is based on the Laplace approximation. When you are in a very high dimensional space, maybe the likelihood to hold a function is very concentrated in a local area. Then you have to really use a large number of samples. Like here, we used about several hundred thousands of samples. So this is a quite large number of samples. Well, so using the Laplace approximation, we can first narrow down where the posterior of the likelihood is. So essentially, first we can compute this so-called map point, maximum posterior point. We can solve this minimization problem where we have the data, and this is the observable map up to the design matrix W, and we have a prior, regularization term. So we can solve this minimization problem. We can get this posterior covariance, which is given as the Hessian of the misfit term is the second order derivative. And then we have the prior covariance inverse. So this is a posterior. And in the computation of the posterior, for instance, if we are in function space, and this is a second order operator, right? So this is actually to compute this posterior is quite expensive. Um, so in one of the approximation, we use the so-called Gauss-Newton approximation. This is the first order derivative, this Jacobian transpose, and here you have a Jacobian. So we can use essentially this first order approximation to approximate this Hessian, and secondly, we can perform a low rank approximation of this Hessian. So in here, we can use some randomized algorithm like randomized eigensolver to solve this generalized eigenvalue problem, where on the left, you have the data related term. On the right, you have the prior information related term. So this eigenvalue, it indicates the relative sensitivity of the directions, corresponding eigendirections psi I. So if lambda I is quite big, that means the data tells you a lot. So you're going to use this psi I. If lambda becomes very small, then that means the data doesn't really tell you so much in the corresponding direction psi I. I mean, if this lambda I decays pretty fast, which is often the case in our test problems. Um, then we can truncate it with a relatively small number of eigenbases, right? So, well, this is a Laplace approximation. If we directly apply this Laplace approximation and compute this EIG under the assumption that we have a Gaussian prior, we have a Gaussian posterior, which is given by the Laplace approximation, then this EIG can be properly approximated by this eigenvalues and also this map point that we computed. So, but here, all these eigenvalues, lambda I and the map point, they will depend on the data and design because when you solve the inverse problem or optimization problem, it depends on the data Y and also the design. And this Hessian term also depends on, this W here. But if you use a Gauss-Newton approximation, then it's free of data. Well, so here, when you have this sort of like the approximate explicit formula for the EIG, you can directly evaluate it, right? For linear and Bayes inverse problems, which basically have a linear map from the parameter to the observable, then this boils down to the so-called D-optimality. So you get a sum of the log of the certain optimality, which is D-optimality, and you can compute it by the corresponding eigenvalues lambda I. And for the linear inverse problem with the low rank approximation, by the way, for the linear approximation problem, this Gauss-Newton Hessian is exactly the same as the Hessian because the map is linear. Right, so then we have the upper bound for the low rank approximation of this EIG is upper bounded by sum of the log of the eigenvalues. Suppose you have the eigenvalues decay pretty fast, and then this term becomes quite small, right? This log term becomes very small. You truncate it up to R term. So relatively speaking, you can compute, this EIG with essentially solving our eigenbasis by randomized eigenvalue problem.
Do you need an expectation there in this bound on the right hand side?
That's a good question. So expectation will be taken with respect to because this is a linear problem, it's a free of data, right? The posterior is free of data.
Mm-hmm.
Uh, right, but yeah, so there is of course there is a certain approximation coming from the randomized SVD.
Yeah, because
Um,
for psi itself, you need the expectation. So I would expect that for the bound,
right.
you will need it as well, right?
Um, for the bound here, right? So when
Yes,
we take
yes.
expectation with respect to the randomized SVD, um, yeah, so we didn't consider this randomized SVD effect. So suppose we have this low rank approximation, right? So, or maybe another way, um, in here, when you compute this eigenbasis, there is a certain error, and this error can be properly bounded. This is by randomized SVD, right? So,
I was
the,
talking about the lambdas, the lambdas being random themselves, right?
right. So, well, yeah, I mean, the lambda will depend on, right? The lambda will depends on other factors. But here, for each specific scenario, we have this specific computation of this lambda.
Okay.
So this is let's say sample-wise bound.
All right.
Okay, thank you. Well, so for like nonlinear problems, you can really compute just simply this term. You have to compute the map point. The map point will now depends on the data, and um, yeah. So you can see here for this linear part, this lambda. Well, when you compute this lambda, you do need to compute from the random samples, like randomized SVD will depend on the random samples. And in there, lambda are random. But this randomized SVD is relatively accurate in terms of, there is a certain error bound depending on the number of samples, depending on the decay of the eigenvalues, essentially the trailing of the eigenvalues. But we didn't consider that part of their error bound. But in the nonlinear problems, and then we also have this map point involved. Uh, So each of the computation for each of the y and w, then we have to compute one map point, right? That becomes quite expensive actually. And for each of the y and w, we also need to evaluate the eigenvalues. Essentially, we need to solve this eigenvalue problem. So in this paper, we proposed to replace this map point simply by the prior points, which generate the data here, y. Because as you can imagine, once you have enough observations, enough data with relatively small noise, then this map point is going to approximate your prior point. So it's rather a crude approximation if you simply replace this map point by the prior points, right? But what you care about is actually the correlation of this EIG with this approximation. In fact, we did some like correlation analysis. So these two terms are highly correlated. Then we can replace simply by the prior points, and then we don't have to solve, this inverse problems here anymore, and we can directly compute, the eigenvalues. Uh, and also, with this prior points approximation, we also performed some like offline online decomposition, because we still need to evaluate this eigenpairs by solving this eigenvalue problems. So by properly rearrange this term, we can pop out this design matrix, and then we only need to solve a small number of generalized eigenvalue problems. And so once we solve it offline, every time in online computation, we can simply assemble this matrix without any PDE solve, and we can solve this generalized eigenvalue problem, which becomes a small scale, essentially becomes R dimensional. And so with this offline online decomposition and some new algorithms, the swapping greedy algorithm, we can solve this nonlinear Bayesian OED problem efficiently. Okay, so but however, still, I mean, you're applying this approximation, right? The approximation of the prior points to their map point. Let's say if you want to compute the map point, for some of the problem, like for high frequency problem, the Helmholtz equations, we found that the correlation is actually not so good, not very highly correlated. So we need to compute this map point essentially. So in order to compute efficiently the eigenvalues and the map point, uh, essentially we need to evaluate, this forward map from the parameter to observable map, and also we need to evaluate this Jacobian, right? So suppose we have a good surrogate to approximate both the forward map and this Jacobian, and then we can compute this lambda and the theta very efficiently before we evaluate this EIG, right? So this is where we proposed, the so-called derivative informed neural operator. In the training of the neural network, it's the same architecture, it's the same dimension reduction, but what's different is, you simply add this term. This term is the match of the Jacobian information. We have the Jacobian from the full map and Jacobian from the neural network map, and it's measured in Hilbert-Smith norm. But thanks to this dimension reduction, we can reduce this computation of the full Jacobian, which is on quite large scale. Now we can reduce it to relatively small dimensions. Like we can compute this reduced Jacobian information, and this part is simply the derivative of the output of the neural network with respect to the input of the neural network. This would be the Jacobian of our neural network. So by this dimension reduction, we can efficiently compute this loss function, and the training of this neural network, a so-called derivative informed neural network, also becomes quite efficient. So we also generalize it to some other neural operator like a DeepNet here, and also some Fourier neural operator, by using this derivative information or directional derivative information. So now, well, because of this dimension reduction, let's say we can project the parameter in the active subspace. Let's say here, this basis are from the active subspace. We get a projected, parameter, which is relatively in low dimensions in theta R. And we can solve this map point problem also in the reduced dimension. So here you have the neural network surrogate in place of the full observable map, right? So the input would be the relatively low dimensional parameter theta R, And also the prior term becomes this is simply the Euclidean norm of the theta r. So to solve this problem, it becomes quite cheap, essentially. You don't have to evaluate the full model. And you can use ADAM or BFGS with automatic differentiation. And so you can compute this gradient efficiently. The gradient of the neural network here is also reliable. It's reliable corresponding to the full Jacobian as you train it here, right? So um, now, once we solve this, map point in the reducer space, we can reconstruct it in the full space. Like here, this is let's say in the active subspace, we have the basis. We can, you know, um, lift it to the original dimensions. But now, we care about the error here committed, like the map point and the approximated map point computed by the neural network, right? So what's this error? How can we bound it? And well, this bound again, so it is a for each of the let's say data y and for each of the design, right? For each data y, each design, we would have a given here this map point, and we want to bound this map point uh, for a point-wise and y and design. So a bit of the transformation. We can first do the whitening of the parameter representation. So this parameter theta, it follows the prior distribution, right? So we can represented as in this form. This is a prior square root of the prior covariance, and this eta follows a Gaussian distribution. Now, we can formulate the map point optimization problem, um, with respect to eta here. In the high fidelity approximation, let's say in the finite element approximation, this is our optimization problem, where theta depends on our eta, right? So, and correspondingly, we have a neural surrogate objective function for the map point of eta hat and star. And this is the reduced the neural network approximated objective function. So this is the two objective functions. Under proper assumption of this, and another quantity is we have this projection. Suppose we have this input projection of our parameter. So under proper assumptions, so essentially we assume that the gradient of this objective function of the high fidelity and approximate that allow convergent Taylor approximation, Taylor expansion around this map point. And also, if we assume that this forward map, the approximation error is upper bounded by epsilon 1, and the Jacobian can be upper bounded by epsilon 2. And then also, if the projection error at I minus PR stands for the projection, it's coming from this basis of a phi R. So if this can be upper bounded by another, tolerance, let's say epsilon 3. But of course, this epsilons that depends on how many training data you would have, what is the dimension you want to project to, right? So suppose we have this bound, and then the map point can be properly bounded. Essentially, we have the theta star and theta hat star. These are the map point in their parameter space, and this is in the whitened space. If we measured in the C prior inverse norm, then it's corresponding to this eta measured in the Euclidean norm. Then this can be upper bounded by this is refactors up to a certain constant. Again, this bound is for each specific data y and a design w. Okay, so here's some numerical evidence. Let's say we see one by one. So this is a solid blue line here is the error for the forward map F. And with increasing number of training samples, like from about 200 to 1,000, we can see decreasing error of the approximation for our observable, right? But this is constructed with the Jacobian information or with the derivative information. If we do not use the derivative information, here is a dashed blue line. As you can see, especially for relatively small number of data, then the error is pretty big, right? So this is for the observable map, and this is for the Jacobian. So so here in the solid line, this Jacobian, as you can see, it also error decays with respect to the number of samples. And the dashed line stands for if you do not train it, then the error is pretty big actually. And then, this is a map point here in the blue line, blue dotted line. If you use the derivative informed training, and you can compute, this is surrogate of the map point and can measure the error. The error is here in the blue line. It can decay with increasing number of training samples. And again, the derivative helps quite a bit compared to if you do not use the derivative training, right? So, well, here's our map point computation. Uh, Here's our prior sample, and we can compute the map point using our DINO derivative informed neural operator of an element. You can see it matches pretty well, and this is a relative error here with a smaller magnitude. And this is for one of the test sample in our distribution. This is another test sample out of the distribution. So this is a Gaussian random field. This is so-called like the truncated Gaussian random field. It's not exactly from the same distribution. It's kind of like out of distribution sample. And we also tested their neural surrogate and the high fidelity approximation. It matches pretty well again. Well, that is for the map point. So here is for the eigenvalues. Instead of solving the larger scale, eigenvalue problem as we presented here, this is in the original space. It's quite high dimensional. It's a generalized eigenvalue problem. After the dimension reduction and also after the neural network surrogate model, we only need to compute this Jacobian here of the neural network, right? Instead of the full Jacobian. And this generalized eigenvalue problem becomes an eigenvalue problem with a dimension reduction. So this eigenvalue problem is now the size of r theta by r theta, which is input dimension of the dimension reduction. So you can solve this generalized eigenvalue problem. Now it's eigenvalue problem very efficiently because you can evaluate this H matrix quite efficiently. The Jacobian is simply approximated by a neural network, right? So now, under additional assumption where you have the Jacobian and approximate Jacobian, so if it is a Lipschitz continuous up to a certain Lipschitz constant here, and then we can also bound their eigenvalues and approximate eigenvalues for each of the component by, also this is three errors, the error for the approximation of the map of the Jacobian and also the dimension reduction with some different constant C1, C2, and C3 head. This is for each of the eigenvalues. All right,
So,
so
good
yeah, go ahead.
question. Yeah,
Yeah,
regarding eigenvalues, right? I mean, sometimes the issue with eigenvalues is that they may be continuous functions of the matrix, but not differentiable, particularly when you have eigenvalues that are multiple, right? I mean, in that
right.
case, we
Yeah.
would not. So how do you deal with these things, if at all they appear in your computations? Maybe they don't, but I just wanted to
Well,
know.
yeah, which is so here, sorry, is we just need to compute this eigenvalues, right? We don't have to let's say differentiate through this eigen. Though we have some other work on where we can differentiate through these eigenvalues, but if the eigenvalues becomes multiple, then it becomes tricky. Then we need to properly take care of the corresponding eigenvectors. But here, this is essentially, we just need to evaluate this eigenvalues. These eigenvalues are, after that we can evaluate the EIG here, and then we can apply some greedy algorithm instead of a derivative-based algorithm. So
You're not tracking them somehow. You just compute them and that's it.
yeah, that's right. We just compute it. And as long as we can compute it cheaply, then we can evaluate this EIG many, many times. And then we can apply some greedy algorithm. In fact, we applied some swapping greedy algorithm. Um,
Thank you.
yeah, thank you. Okay, so this is about the match of the eigenvalues computed by a neural network and also finite element. So as you can see, the solid line stands for the finite element, dashed line stands for the neural network, and we have about three different samples. Essentially, we have three different samples of the data and the design metrics, and as you can see, they match with each other pretty well, especially for the leading eigenvalues, right? So okay, so eventually, we computed this eigenvalue approximation and also this map point approximation. We have our, EIG information, which is, dependent on this eigenvalues and also the map point. So we can also properly bound the approximation of this EIG, and eventually it will depend on the error for the eigenvalues and also the error for the map point approximation, where we have the error derived here for the eigenvalues and also the error derived for the map point, and eventually we can bound this approximation error. Okay, so with the bound of this approximation error, let's see how does it perform. So on the left, we computed the D-optimality, which just depend on the eigenvalues, right? On the right, we also computed their EIG. So on the left, you can see in the blue dots, those are the computations over a certain number of samples, let's say 100 samples. And you have the neural network evaluation of the EIG, and also you have the neural network that is trained without Jacobian. As you can see here, if trained with Jacobian, then the approximation error is actually quite small compared to the final element and the neural network. You have about a 3% of approximation error. And this is a standard deviation of the approximation. And without using this derivative information in your training of the neural network, you can commit quite a large error for the neural network and final element comparison, right? So this is similar for this EIG computation. And in the EIG computation, the error is even smaller. It's about 1% compared to about 18% of the EIG evaluation. And visually, you can see a much higher correlation of the DINO compared to the neural network without Jacobian evaluation, with R score quite close to 1 here for the DINO. Okay, so we also did some scalability test. If we increase the parameter dimension in the high fidelity approximation, let's say we use 32 by 32, 64 by 30, 64, and 128 by 128, and we can approximate these different quantities, the observable map, the Jacobian, and also the map point. As you can see here, there is not so much difference, right? With increase in training and size, we can actually get a pretty much the same accuracy for, let's say, this map point. Sorry, so for this forward map and Jacobian here, and the map point is subject to the optimization, and there is a fluctuation, a little fluctuation of this optimization with respect to the map point. And here is a computation for the eigenvalue problem. As you can see, with increasing dimension, then the neural network approximation and the final element, they also match pretty well for different measure size. Okay, well, it's already 50 minutes. Well, so here's some of the comparison on the computational cost. Let's say let's take a look at this 3D example, 3D convection fusion reaction problem. Here we have a finite element approximation. We have a neural network approximation. This is the evaluation time of the finite element. As you can see, evaluation of the parameter to operator map, observable map, and map point, and also eigenpairs. You have about several hundreds up to thousands of speed up. And we also take into account our offline and training time, computation time. Like we need to compute the reduced basis. We need to compute the offline and training data of the map of the Jacobian, and this is the total cost, and this is the training time. So by taking account this offline computation and training time, then we can deploy our surrogate into the online computation in the greedy algorithm, right? So in the greedy algorithm, we need to evaluate the EIG for many times. Let's say for the 3D problem, we need to evaluate about 1.5 million times. And then in total, we're going to achieve about, we achieved about 1,000 speed up by accounting for this offline computational cost. Sorry, I'm not doing well on time, but for the last part on the sequential optimal experimental design and some neural network structure, I think I'll leave it here. If you are interested, then we can talk more about it. Yeah, so the take-home message is essentially, the derivative informed neural operator or neural surrogate they're accurate for both the input-output map and also for the derivative information. And the reduced basis architecture with dimension reduction can make the derivative training scalable, and computation of the data also becomes scalable. And then, so as you can see from the plots, where we use relatively small number of training data to achieve high accuracy compared to if we do not use the derivative training, right? And so with the neural network approximation, we can evaluate the EIG and solve the experimental design problem in a fast and scalable way. And that's about it. Thank you very much.